Okay, today we're going to talk about probability. Let's get started. So we're going to learn to find the probabilities of events. We're going to learn to find the probabilities of mutually exclusive events, of independent events, and of the complement of an event. So let's get started with talking about some definitions. So way back in middle school when you talked about probability, you also probably talked about odds. And one of the ways that I like to explain probability is the number of things you want divided by the total number of things, where odds is the number of things you want divided by the number of things you don't want, okay? So the answers for probability always range from 0 to 1, where odds could be greater than 1, okay? So, excuse me, probability is always positive, and the answers are always between 0 and 1 because it's like a percentage, okay? Now, some other terms we need to be familiar with that are going to be used in this section. And you may have already heard these terms, but let's refresh everybody's memory. So the first term is experiment. And an experiment is something that happens that has an uncertain outcome or an uncertain result. Okay? So, and it means, you know, any type of test that you're doing. Okay? And then another term is called sample space, and this is the set of all possible outcomes of an experiment, okay? And then finally the term event, and the book defined event as any sub-collection of a sample space, which really doesn't give you a good idea of what it is they're talking about. So if you want to think of an event is a single outcome of the sample space type thing, okay? So that may be a better definition for you. It's not exact, but it gives you an idea of what we're talking about when we say event in mathematics. So let's first talk about what a sample space is. When we are talking about a sample space, remember that's the list of all the possible outcomes. So if we want to determine a sample space, that means we have to list all the possible outcomes for our particular experiment. So let's do a couple examples. When we toss a six-sided die, what is the sample space? Well, the sample space, S, is going to be all 6 possible things that could happen. Well, it could land on 1, it could land on 2, 3, 4, 5, or 6. Okay? So that is the list of the sample space. If we are looking at it, it's got 6 different possibilities, and they are the numbers 1, 2, 3, 4, 5, and 6. Okay? So when you toss a coin, what is the sample space? Well, my sample space is going to be either heads or tails, right? So this has 2 different outcomes, heads or tails. Now let's talk about probability. If an event, and we're going to call that event E, has n number of equally likely outcomes, and we refer to this as n of e, right? It's kind of like a function. Has n equally likely outcomes, and its sample space S has another number, n, of equally likely outcomes, then the probability that event E could happen is going to be n of big E divided by n of S, which doesn't really tell you much, so let's talk about what that means. So n of E is the number of ways E could happen, okay, so what you want, divided by the number of items in the sample space, which is why we counted how many items were in our sample space, because that is the total number of items in our sample space when we count them all, okay? So divided by the number of items in the sample space, which is our total. Okay, so let's do some practice with this as well. So if a coin is tossed, find the probability that it lands heads up. So remember, probability is what you want over the total, right? So what you want is heads, right? Well, that's one particular configuration out of 2 items in the sample space, right? So the probability is 0.5 or 50%, right? If 2 coins are tossed, find the probability that they both land heads up. Now this is a slightly more complex thing, okay? Because now we not only have 1 coin, we want we have 2 as well, okay? So my event is that I want a head for the first coin and a head for the second coin, right? Okay. Well, the sample space, when we calculate this out, I could have both of them be heads. I could have the first one be heads and the next one be tails. I could have the first one be tails and the next one be heads. Or I could have them, oops, sorry, I'm putting too many commas in here. Or I could have them both be tails, right? Those are the 4 possible outcomes of how I could flip these coins, right? Well, if I want only one of these 4, then my probability of my event happening is 1/4 or 0.25 or 25%, right? So, now we have a slightly more complex one. Here we have 2 6-sided die. We want the probability that they both add up to 11. So we have die 1 and die 2, right? Now, the only way that these 2 die could add up to 11 is if one of the die is 5 and the other die is 6, right? Now, this could happen with die 1 being 5 and die 2 being 6, or it could also happen the opposite way, right? Okay. Now, so that means the probability of this event happening is going to be 2 over some number, okay? Now, what's that number going to be? Well, I have 6 ways that die 1 could come out, okay? So die 1 could be either 1, 2, 3, 4, 5, or 6, right? Now die 2 could be the same, 1 through 6 for the first one, 1 through 6 for the second one. Okay, so each of die 1's configurations could have 6 different die 2 configurations. So that's going to give me 6 times 6, which is 36 different configurations, right? So 2 divided by 36 is 1 over 18, right? So 1 divided by 18 is a 0.055 repeating. Okay, so about 5 or 6%, right? Chance that that if you roll these dice, they'll both total up to 11. Now let's talk about some lottery problem things. Here we have a lottery game, and it requires players to choose 6 numbers from 1 to 50 and match them in any order. And we want to know how many different configurations are possible, right? So when we are talking in any order, that is combinations. So we are taking 50 things 6 at a time, right? So that's 50C6. Now when we put 50C6 into the calculator, we get 1589070. So 890,700 different combinations are possible. Now say we want the same thing, only we want these numbers in a specific order. How many different permutations are there? So this would be 50P6, because order matters for this. So each different each of our numbers has to be in that specific order. So we're going to do 50P6. And we get a much larger number, 11441304000, right? So basically 11,441,304,000 different configurations if we have 6 numbers in a specific order from 1 to 50, okay? So if you're out there playing any lottery games once you turn 18, be aware that if you are required to play numbers in a specific order, then your chances are much less than if it's in any order, okay? So, say you buy one ticket at random, okay? Your probability is going to be 1 over however many total different combinations. So 1 over the 15,890,700 is going to be going to be equal to 0.3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 0.00000063, right? So that is really, really tiny chance that that one ticket will win. Well, if we did the same thing with the other type of ticket, that's the probability would be 1 over your 11 billion. And that is, resorting to scientific notation, 8.74 times 10 to the negative 11th. Doesn't look like an 11, but it's supposed to be an 11. Times 10 to the negative 11. Okay, so your odds, your probability of winning the lottery goes down drastically, okay? This is 6.3 times 10 to the negative 8th, whereas that is 8.74 times 10 to the negative 11th. You already have pretty slim probability that you would win anyways, but it goes down even further once we say, hey, the numbers have to be in a specific order. So now let's talk about some other types of events that could happen. Two events are considered mutually exclusive if they have no outcomes in common. Now, what this means is, an example is, you cannot attend school as yourself cannot attend school and stay home at the same time. You can't be in two places, right? So the events attending school and staying home are mutually exclusive for one person, right? You have to be somewhere. You can't be in two places at once. Okay, so that's an idea of what mutually exclusive means. Okay, so the probability of two mutually exclusive events happening at the same time is 0, right? So we refer to this as the probability of A intersection B. Okay, and that's what this little upside down U is, intersection. And you can see these events are mutually exclusive. They don't cross over each other like Venn diagrams normally would. There is no intersection, so the probability that that would happen is 0. Now let's talk about the probability of the union of two events. If two events are in the same sample space, the probability of either event A happening or event B happening is given by probability of A union B. So unions are more like ORs, and intersection is an AND, okay? So the probability, and remember in a previous video I said AND means multiply and OR means add. Here's what we're talking about with that. So the probability of A union B happening is the probability of A plus the probability of B, right? I just noticed a typo here. And it's probability of A plus the probability of B minus the probability of their intersection. So what we're saying is we're taking, if we've got a sample space here, right? We've got all these different things in A, all these different things in B, and some of these things are in both A and B, okay? And then we have, things out in our sample space too. Okay, so if we're looking at this, we want all the things in A, right? The probability of that happening, plus all the things in B, right? Well, now, since we're looking at these things in the middle. We've double counted them. So whatever is in that intersection area, we have to subtract out so we don't double count them. So that's why our formula is probability of A plus the probability of B minus the probability of their intersection, okay? Now, if two events are mutually exclusive and we want to know the probability that either event A or event B will happen, remember the union is or, then that is going to be the probability of A plus the probability of B, okay? Now, notice there's no intersection here, right? So we don't need to subtract out things that were double counted. So that's why this formula is a little bit different from the one above it. So the probability of the union of two events. A 20-sided die is rolled. What is the probability that the number is either even or 7, right? So the probability of even or 7. Now, or is union, right? So we want the probability that it's even union with the probability that it is 7, right? So if we're looking in the sample space of my die, right, I want it to either be even, which is 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, right? Or the probability that it's 7, right? Now, these are two mutually exclusive events, right? So the total number of die roll that could happen is it could be either the even ones, it could be 7, but it could also be 1, 3, 5, 9, 13, 15, 17, or 19, right? Okay. So the probability that it's even, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those, right? Divided by the 20 that I could have, plus the probability of that it could be a 7, which is 7 over 20, right? So 10 20ths plus 7 20ths is, or sorry, not 7, 1. There's only one 7, right? Make sure you don't make that mistake, right? Okay, I caught myself in the middle of it. It's not that we have 7 possibilities. We only have one, and that's that it could be 7. So 10 plus 1 would be 11 different configurations over 20. Which is about a 55% chance, okay? Now let's talk about independent versus dependent events. Two events are considered independent if the occurrence of one has no effect on the occurrence of the other. So an example of independent versus dependent events, if you have two dependent events, that means if one happens, that could cause the other to happen, okay? Say you're measuring the amount of temperature in a room and determining whether, and you're also measuring whether the window is open or not. Well, the window being open or not could cause the temperature in the room to change. So those would be two dependent events, okay, versus measuring two things that really don't have any relation to each other, okay? So, and if they have no relation to each other, then they're considered independent events. Now, finding the probability of two independent events would happen, A and B would be probability of A times the probability of B, okay? And that's your probability of both happening would be probability of A times the probability of B. Now let's talk about the complement of events. The complement of events is the complement of an event is all of the outcomes that are not in A but are still in the sample space. So remember when we had A and B and we had other things off, here in sample space, right? So everything that is not A is everything that's outside of A but still in our sample space. And in this instance, I drew a square around the sample space so that you could see numbers that were in the sample space but not in A. And we denote a complement by saying A prime. So the probability of A prime happening is 1 minus the probability of A happening. So let's do an example of this. Here a manufacturer determines that the probability of a unit having defects, of having a unit with defects is 1 out of 350 units. What is the probability that a lot of 1,000 will have one or more defects? Okay. So these kind of problems require a little bit of backwards thinking, not backwards, kind of twisted, but not in a bad way. So if we are looking at the probability that a unit is defective, that's 1 out of 350, right? Well, what we really want to consider is the probability that a unit is perfect, right? So the probability that a unit is perfect is going to be probability that it's perfect is going to be 349 out of 350, right? Okay, so that's the probability that each unit is perfect. And if we want that to be for 1,000 units, we can take that to the thousandth power, right? So that's the probability that each unit is perfect, right? So the probability that at least one is faulty will be 1 minus the probability that it's perfect. So that will be 1 minus 349 divided by 350 to the 1,000th power, which is 0.9428, I should say. 28, which is 94.28%. Okay, so if 1 out of 350 are defective, that means that you have a 94% chance that a lot of 1,000 will have at least one faulty unit. Okay, so you're going to have a pretty good chance that at least one unit in a lot of 1,000 will be faulty. Okay. So here's what we've learned. We've learned to find the probabilities of events. We've learned to find probabilities of mutually exclusive events, of independent events, and we've even learned a little bit about the complements of events versus probability. So we will do much more of this in class, obviously. See you guys later.